in the first part of this LLM architecture review, we went up to section 2.2, discussing Gemma 3, and we're going to jump right back in by discussing the normalization layer placement in Gemma 3. So in this model, we use RMS norm in both a pre and post norm setting around the GQA module, which is similar to Gemma 2, but still worth highlighting as it differs from like any other paradigm, at least that I've seen before. So in the OMO 27B, where we have the post but pre-residual stream normalization and the QK norm, in Gemma 3, we have the same post RMS norm followed by or preceded by a pre-RMS norm and then a QK norm. So what the author says, and I think is pretty valid, is that the normalization layer placement is a relatively intuitive approach as it gets the best of both worlds, like pre and post norm. And extra normalization can't really hurt because in the worst case, the extra normalization is redundant, which adds a bit of inefficiency to redundancy. And in practice, since RMS norm is relatively cheap in the grand scheme of things, this shouldn't have a noticeable impact unless like you're having a separate kernel being launched specifically for RMS norm and not using some fusing scheme. In that instance, then you are just like making extra burden on your GPU. But going to our summary, it's a well-performing open-way LLM that is underappreciated in open source circles, and the most interesting part for sure is the sliding window attention, which improves efficiency. And Gemma 3 also has the unique normalization layer placement that we just discussed, both before and after the feed-forward and attention modules. And there's also Gemma 3N, which was released recently in order to have an optimized an optimized transformer model for small devices. And I think this is like already running on like the Pixel phones that have just came out. So the change that was made to permit these large models to run on mobile devices is the per layer embedding parameter layers, or rather to offload these layers from the GPU. We just only keep a specific subset on the actual GPU memory, and these token-specific layer embeddings, such as those used for the different modalities, are then streamed from CPU or SSD on demand. And this means that we can go from a 5.44 billion parameter model to a 1.91 billion parameter model, at least in terms of what's actively on the GPU. So this is because the per layer embedding parameters are cached to fast storage, and they're only loaded upon demand. So this is from the Gemma 3N blog. What is worth noting here, though, is I thought it was a 4 billion parameter model. Where is this 5.44b coming from? And this is because Google and others have an interesting way of reporting the parameter count in LLMs, where they exclude the embedding parameters to make the model appear smaller, except in cases like this, where it is actually convenient to make them appear larger, since you'll have a larger difference between your cached and skipped parameter model versus your standard one. So this is, however, not unique to Google because it's a common practice across the field. And another thing which I discovered while reading this is something called the matformer concept, which it means that we can like split up our transformer into blocks that are themselves usable. So Gemma 3N uses a single shared LLM transformer that can be sliced into smaller independently usable modules, and each slice is trained to function on its own. So at inference time, you can just run the part you need instead of a larger model. So perhaps based on the modality, you can run a specific subset of the transformer, which is, it's quite compelling. Moving on, Mistral Small 3.1, which is, I guess, a direct competitor to Gemma 27B, which is why they're compared. So this was released in March, shortly after Gemma 3, and it outperforms Gemma 3 on several benchmarks except for math, while being faster. And the reason why it's faster is because it has less transformer blocks. At least that's one of the reasons why. So if we look here, we have 40 transformer blocks in the right and 62 on the left. So less forward and backward pass, or at inference, less forward passes means you get faster inference. And other ways that it's faster in terms of latency is a custom tokenizer as well as a smaller KV cache, but it's a standard architecture otherwise, which is dense. So if you'd like to look at the specific parameters, then please pause the video. And earlier Mistral models had utilized sliding window attention, but they have abandoned it in Mistral Small 3.1. So since Mistral uses regular group tree attention instead of group tree attention with the sliding window, as in Gemma 3, maybe there are additional inference compute savings due to using more optimized code, such as fuse kernels with flash attention. And furthermore, sliding window attention is more of a memory usage reduction technique as opposed to a latency enabler. So this is what Mistral 3.1 Small focused on. That is to say, improving inference token generation. So we have, I guess, 3 more models: Llama 4, then the Quens, and then K2, or Kimi 2 rather. So the extensive introduction, or I don't know how extensive it really was, but the discussion of a mixture of experts will motivate the discussion of Llama 4 since it is a sparse model. So first of all, Llama 4 uses group tree attention, which is similar to its predecessors, whereas if you compare it to DeepSeek v3, we have the multi-head latent attention. And they're both very large, with DeepSeek v3 having 671 billion total parameters and Llama 4 having 405. But when we look at the active parameters, DeepSeek v3 has twice, as opposed to, or almost twice, as opposed to 17 billion active parameters for Llama 4. So it's actually still larger for DeepSeek in both instances, but the difference is larger when you look at the active parameters versus the total parameters, because it's 68% larger in the total parameter count, but almost twice as large in the active parameter count. Llama 4, as opposed to DeepSeek, uses a more classic mixture of expert setup with fewer but larger experts, so 2 active experts with an 8,192 dimensional up projection, as opposed to the embedding dimension, which is 5,120. So I don't know if that's legit, because that's a strange up projection, but perhaps that's the ratio that was chosen. I didn't think that you could do like fractional ratios for the up and down projection matrices, but we have, once again, 128 experts, so half of the experts as is DeepSeek, and then 1 shared and 1 expert active per token. Also, whereas DeepSeek uses a MOE layer in each transformable block except the first 3, Llama 4 alternates mixture of expert and dense models in every other transformable block. So it's not all mixture of expert. And in half of the blocks, of which there are 48, you actually have a dense model. So 24 out of the 48 are just dense feed-forward layers. And now, let's discuss Qwen 3, which will then lead us into small LLM3, which is the one I forgot, and then KM2. So there are 7 dense models and 2 mixture of experts models, ranging from 0.6 to 32 billion for dense, and then 30 to 235 billion in the sparse space. So beginning first with the dense models, the smallest is 0.6 billion parameters, or 600 million. And in the personal experience of the author, it performs well, which means for him that it's like the best kind of tinkering model, even better than Llama 3.2 1B. And if you look at the differences, you can see that it's a deeper model, almost twice as deep. And it makes up for this by having a smaller number of heads and a half of the dimension size and a smaller hidden layer up projection as well. So you can see that these are the trade-offs that you have to make if you want to have a deeper model in terms of the number of transformer blocks. And you can see here some performance numbers on tokens per second and memory usage. So we can see that the Qwen 3 model has a lower or higher latency, but a lower memory usage on an A100 GPU. And the reason for this is that it uses more transformer blocks than Llama 3, which leads to a slower runtime, but is, of course, 60% of the size of Llama, so has a smaller memory footprint. So this is one trade-off between the two. If you want higher latency, then probably go ahead if you want lower latency, then get the Llama set of models. But if you have if you're in a memory bounded, regime, then go ahead with the Qwen 0.6 model. Okay, now let's move on to the mixture of experts models, which are more interesting. First of all, the mixture of expert variants are once again there to make inference better, because you're essentially getting free lunch in the sense that you have a very large model, but you're not using all the parameters. So you still have like the advantage of all that knowledge if your router is competent, while maintaining a low amount of active parameters so that you can actually run the thing on perhaps like a more reasonable cluster than what would be required if you had a dense model. So that's all of what's being said here. And one thing worth noting about the name is that A22B just means 22 billion active parameters, which is less if you compare it to DeepSeek v3, which will be happening here. So when you look at these two diagrams, you can see that they're quite similar, as is mentioned by the author, but you do have different attention mechanisms and then a different mixture of expert regimes. So in Qwen, we have 8 experts with no shared expert. And then in DeepSeek, we have 1 shared expert and 8 experts. So 1 more expert is used in Qwen in DeepSeek as opposed to Qwen. And we also have half of the experts overall in Qwen 235B, 128 compared to 256. The Qwen 3 team did not disclose as the reason why they moved away from shared experts, because it was actually used in the 2.5 series of models. If the author had to guess, he would say that it's due to the improved training stability, and by moving from 2 experts to 8 experts from 2.5 to 3, so it didn't really necessitate the extra one, and also, I guess, extra memory savings as well by using 8 instead of 9, but this does not explain how DeepSeek v3, or why rather DeepSeek v3 is still using the shared expert, and in fact the Kimi K2 model also still uses the shared expert. Whether that's because they empirically see it as better performing or because they just copying DeepSeek, that is unknown. And small 3 is not nearly, small LLM 3 I guess, is not nearly as possible as other LLMs, but it's still interesting if you look at this graph, which has model size versus win rate in LLM benchmarks. So you can see that it is quite well positioned, kind of in between Qwen 3 and Qwen 3 1.7, Qwen 3 4. So if you want a middle model, then take this over Qwen 2.5, 3 billion. And when we discuss the architecture here, it's quite interesting to note that when we compare Qwen 3.4 to small LLM 3B, there is a no positional embedding in every fourth layer. And I think this is kind of a silly name because you're just having nothing. And this just means that we have like no positional embedding. So let me just come to this preview here so that I don't have to cut off the diagram. It's quite hard to print these things out in a PDF. So when you look at our positional embedding, we have the token embeddings themselves here, followed by the positions. So in an absolute positional embedding, you'll have, I guess, a increasing order as you go further into the sequence. And then once you add the positional and token embeddings, you get the input embeddings themselves. So coming back here, Rope does this positional embedding by rotating the key and query vectors relative to their token position, and the position, like absolute positional embeddings like sinusoidal, just add like exactly as done here, a absolute value to each token, which means that it will not be able to scale beyond, or at least not scale well beyond the token or context length of the model that you trained it on. But without going off on a tangent, in Nope, we just literally do not have any token position embedding. And according to the results here, it does perform well. If you look at accuracy and Nope being the purple one, it seems to be above when you compare it on different tasks in varying problem lengths, where overall performance does diminish as the problem gets longer. But I am very suspicious of this, and you can see literally here that it was only tested up to 100 million parameters in size. So it has never been actually verified at scale, and it's most likely for this reason that the small LM3 team only uses it once every fourth layer, I guess just to have less computation. So this is definitely something you can get away with. Like if you just use no positional embeddings whatsoever, then I'm not sure that this will be successful. They do say here that since the model knows which tokens come before others due to the causal attention masking, it does have some notion of the positional information, but it's not explicit, it's rather implicit. And this is just due to the sense of direction baked into model structure, because we only allow tokens to attend to previous ones. So you can like allow the model to learn this causal relationship without giving it positional information, but you're only helping it by doing so. At least this hasn't been tested at scale, is all I'm saying. So that's the last word that I'll leave here. Now let's move on to Kimi 2, which made big waves by being the kind of first open weight model, to be honest, to rival the big proprietary models. Of course, there was DeepSeek, but this one is like pretty good. Like it's pretty impressive. First of all, it uses the Muon optimizer, which was popularized by Keller Jordan using his kind of speed running benchmark, as opposed to Adam with weight decay. And this was the first time it was proved up to scale, with the previous time being only up to a 16 million parameter. And it resulted in a very nice loss curve, which has helped the model be like at the top of many benchmarks or near the top. And those loss curves you can see here. So the Kimi 2 training loss curve does look quite consistent, and you can see that it is quite monotonic in its decrease. And this trains up all the way to 15 trillion tokens, which is very impressive. And they also have the OMO and OMO 2 training loss curves for some reason. I'm not sure exactly why. The model itself is 1 trillion parameters, which is definitely impressive. And it's the biggest LLM of the generation if you consider only open source LLMs and not the switch transformer, which was an encoder-decoder architecture transformer made in 2021, mostly for the translation and BERT set of models and T5. So it's not really comparable to the current generation of models. So if you don't consider that one, then it's literally the biggest open source model that exists. And if you consider it to the closest thing to it, which is definitely what inspired it, DeepSeek v3/R1, then you'll notice that it is similar despite having fewer heads and more experts. So this is kind of the difference, where you look at more experts here and fewer heads here. So they really highlighted it. And the last block says that whereas DeepSeek has the first 3 blocks using an FFN within size 18,000 432 instead of the mixture of expert model. The Kimi K2 model only has the first block using a dense feed-forward network and every subsequent one using a sparse mixture of expert feed-forward neural network. So Kimi K2.5, or rather Kimi K2, this is a typo, is quite similar to DeepSeek V3, except that it's scaled and uses more experts. What I didn't know is that Kimi 2 is not something which came out of nowhere. Of course, it is the second or rather third iteration if we assume that they did 1.5, and then 2. But the problem was that 1.5 was released on the same day as DeepSeek R1, which definitely clouded it on January 22nd. And also, they never released their weights publicly. So the Kimi K2 team most likely took these lessons to give an open weight model and release it before DeepSeek R2, which is quite a pro move by them to get the attention before DeepSeek makes waves with their next model. And as of writing this and as of making this video, Kimi K2 is the most impressive and most competent open weight model. So that's all for this video. I hope you enjoyed. And if you have comments, then please leave them in the comment section.